So now that we have figured out that we have what's called an impulse, which is applying a force to an object for a certain amount of time, and hopefully what you've realized is that it is this impulse that is what actually causes an object to change its motion, because we are applying a force for a certain amount of time. Okay, something we've not talked about. And what that causes to an object is it causes that object to change its momentum. And by changing its momentum, what we are really changing is the object's velocity. And so these two, impulse is then equal to the change in momentum. Now, what we want to do is we want to find another way to essentially calculate or determine what the impulse is. And that's where we're going to look at what's called area underneath the curve. So, once we now know that a force acting on an object over a given amount of time is an impulse, then one of the things that we assume is that forces are always constant, okay? Which, by the way, is another bad assumption, because they're not always constant, but that's one of the things that we assume, because when we make a calculation, we always get F equal to something. Okay, so let's say you have a 20 Newton force that pushes on a car for 2 seconds. And we want to calculate what the impulse is. Well, that's a real simple calculation. Impulse is force times time, 20 newtons times 2 seconds. That impulse is 40 Newton seconds. We can hammer that out pretty easily. Okay, but we want to look at this another way. Okay, what if you were to graph this data on a force versus time graph? What would that actually look like? So, here's my graph. I have a force and I have time. What would a constant force of 20 newtons look like? Well, that constant force of 20 newtons would look like a straight line. Okay? And that would happen for a time period of 2 seconds. Well, if you look at this graph, I have this area underneath this curve. And we did this a while ago with distance and velocity graphs. Okay, but I can actually calculate that area. If you look at the area of this, the area is the length times the width. Okay, and the length is time, the width is force, so that's just force times time. So essentially what happens is the area under this curve is equal to the impulse that is acting on an object. And this would be another way that we could actually determine what impulse is. Now, in looking at this, one of the things I said is forces are not always constant. So, we're not always going to have a force versus time graph that is a nice straight line. We might have a force versus time graph that looks like that. We might have a force versus time graph that looks like this. Okay, we might also have a force versus time graph that looks like this. Okay, and we actually could have a force versus time graph that goes underneath as well. Okay, but that one doesn't happen too often. But there's lots of different variations for force versus time graphs. So, what if we want to find the impulse, okay, under a force versus time graph that looks like this? Okay, and I'm just going to throw a force here. So let's keep 20 newtons as my force that is applied there for a time of 2 seconds again. Okay, how am I going to find the area under here? Well, essentially, this is a triangle. So, in order to find the area under this curve, we'd use the area of a triangle, which is 1/2 base times height. Okay, the base and the height are still force, and time. Okay, so I still have my units of impulse. I'm just calculating the area underneath that. So that area would be 1/2. In this case, the base is 2 and the height is 20. So the area would be 20 Newton seconds. And I always should put in units, newtons and seconds. Okay, so we would just find the area of the triangle then. Okay, so that's essentially it. The only difference is you can have force versus time graphs that look something like this, where what you may have to do is cut this apart into 3 different areas: area 1, area 2, and area 3. And in order to calculate the impulse, what you would do is you would calculate the area under each little section. Okay, so the impulse would be the area under section 1, and then you would add the area of section 2, and then you add the area of section 3. Okay, so area 1 would be 1/2 base times height, because it's a triangle. Area 2 would just be base times height, because it's a rectangle. And then area 3 again would be 1/2 base times height. So you would just calculate out those separate areas. One thing to think about, though, is what your base is in each case, because I know students have had issues with this. This base is only 3 seconds. Okay, this base here is only 6 seconds. Okay, and then this base here again is only 3 seconds. So make sure you're paying attention to what your actual bases are. Okay, now in the real world, okay, you're going to get some things that are going to look like this. Okay, and they're not even going to be this perfect. Okay, but you have a triangle here where you still want to just calculate the area by using 1/2 base times height. Okay, and again, paying attention to what is your base. And your base here is just 5 seconds. And your height is 10 newtons. So the area here of this triangle is 1/2 of 10 times 5. So that area is going to be 25 Newton seconds. Okay? Now, getting closer to the real world, okay, you're going to have more things like this. Okay, and this is actually what you're going to see in the lab that we're going to do on Monday, right when you get back. Okay, we're going to do a lab on bungee jumping trolls, and we are going to figure out what the impulse is on when you bungee jump. But this would be a real world situation where you actually have, this is actually an impulse graph of something like a ball that's hitting a wall, or it could be a bat that's hitting a ball. And what happens in those types of situations is there is a max compression point that we get to, so that force is not constant during the whole entire motion. There's just some max force that it gets to, and then the force increases along here, and then as the ball is leaving the bat or racket or whatever, that force decreases. So we get graphs that look like this, and then we have to ask the question, well, how are we going to calculate that? Well, the best way to do that is to get a best approximation of a triangle, and so we make a triangle out of this, okay, just like this previous one, which is why I kind of showed you this one. So you can make a triangle out of this, and then technically this area that's right here is replaced by this area, and this area that's out here is replaced by that area, and it's a good approximation. So we can use that to calculate an area. The other thing is, look at our time units. One of the things you're going to have to pay attention to are time units. This time is in milliseconds. So there's a conversion we're going to need. 1 second is equal to 1,000 milliseconds. And crashes and balls hitting bats and a tennis ball hitting a tennis racket or a golf ball hitting a golf club hitting a golf ball, I should say, all those time frames are milliseconds. But if you were to graph every single one of those, okay, they all look something like this. And you'll see this in the lab that we'll do. So what you're going to do for a homework assignment is you are just going to calculate some areas underneath some curves. Very simple and straightforward. Okay, I wanted to show you this, but it didn't come out very well. This is a force versus time graph for, and I know you can't read this, this is an egg hitting a wall. And so if an egg goes up and hits the wall, it's got a very, very short time. Okay? But if you take that same egg and you throw it on a bed, okay, that is going to be a much longer time period. And that's actually one of the things we're going to test in the lab. So sorry that didn't show up. But what you have is a homework assignment where you're just going to calculate the area under some force versus time graphs.